absolutely terrified of people because there were no mammals on New Zealand, you know, until the 1100s, when people first came. And so they're very curious, and they'll land on your shoulder, they'll land on your toes, and they'll walk along like a dog when you take a walk, following you. So they're my favorite bird. Had to say that. Anyway, the dinosaurs amongst us. Let's just get into it. You know, most people nowadays have heard that birds evolved from dinosaurs, but that's not a phrase that I like at all. I think there's two things wrong with that phrase. First off, it implies that birds are very different than dinosaurs. They evolved from them. They're no longer dinosaurs. And two, it suggests to me when I hear that, that they came after dinosaurs or at the very end of dinosaurs, when in fact, they lived for almost 100 million years with dinosaurs. So they really coexisted for a long time. Anyway, what I hope you get out of this talk more than anything is both how dinosaur-like birds are, but also how bird-like dinosaurs were. And you'll see the commonalities and why most people believe now that, most paleontologists believe that birds evolved from dinosaurs. Move that. Hope I don't need it. Okay, I got to figure out how this mouse works. I haven't tried this yet. Make sure I'm doing the right way. How does this mouse work?
Yeah, you can just go down.
Okay, I can do it this way.
Yep.
Down works or
Yep.
sideways? Down.
You can go down.
What to do?
Oops.
I'll let you fix that.
All right.
It's always red.
Here you go.
Now what do I do?
Just click right there.
I can click right there. That'll work. Okay. Well, before we do anything else, the first thing I want to do is I want to talk about what makes an animal a bird. What makes birds different than other living animals? Okay, so let's start off by doing that. If we're going to talk about how dinosaurs evolved into birds, we have to start off with what is a bird anyway. So move this over here because I'm a lefty. Here we go. What distinguishes birds from other living vertebrates? First off, they have wings. Now, notice that that's in regular sentence font. That means that it's a 95% true statement. If it's a 100% true statement, I put it all in caps. But 95%, it's 95% true that birds have wings and other animals don't, other vertebrates don't. But of course, there are bats, right? So it's not 100% true. However, to be fair, the wings of bats are what we call analogous to bird wings. They're very, very different. They serve the same function, but they're not the same structure at all. So as I'm sure you know, if you were to look at a bird's wing, basically what you've got is you've got its arm and its hand, and you've got stiff feathers coming off of its whole arm and hand. On the other hand, if you look at that wing, well, actually here we've got birds, pterosaurs, and a bat. So we just talked about bird wings. Pterosaurs, which we'll talk about in a little bit, they were much more like bats. They had a flap of skin that extended from a very elongated pinky. Okay, there was this flap of skin hanging off this incredibly long pinky, so it's not at all related to a bird wing. And bats use all 5 of their fingers. Okay, they take their fingers like this, and there's a flap of skin that those fingers support. So bats have wings, but really very, very different than bird wings. Second way that birds are different from other living vertebrates is that they have a hard, toothless beak. It's part of what we associate with birds. However, only 95% true because turtles also have hard, toothless beaks. So it's not 100% true. It's also not 100% true, though it's largely true, because not all birds, like this a turkey vulture, not all birds have a completely hard, bony beak. You can see that the top half of its beak is actually quite soft and fleshy, and it's only hard at the tip. They are completely toothless, however. Okay, so even though they don't look like they might be. All right, third way birds differ from other living animals is that they have hollow bones. And this is because, and I'll keep coming back to this point, birds are designed to be lightweight. And one way you lose weight is to take your heavy solid bones and make them hollow with struts inside. So there's a human bone, you can see it's very solid with thick walls versus the eagle bone there. Again, I only gave this a 95% true because first off, not all of a bird's bones are hollow, only some of them are. I mean, even if you look at a robin or some small songbird, but there are some birds like kiwis and penguins and ostriches that don't have any hollow bones at all. So it's really not a defining characteristic, but it is true 95% of the time. Oh, goodness. Okay, fourth trait, they lay calciferous eggs. And you all know what a bird egg looks like because we live on chicken eggs. Most of us eat chicken eggs all the time. This really is very distinct because many animals lay soft eggs, jelly-like eggs. These happen to be the frog eggs in water, okay? Very different. And even if you look at lizard eggs or snake eggs, they're very different as well. So on the left, you've got a white-cheeked tern egg or a set of them. And, you can see it looks just like you'd expect. You try to peck your way out and it fractures because it's hard. You've all cracked chicken eggs. Over here, well, you can't see because I don't have a pointer, on the right side, that's a python, a nest of python eggs. And you can see by looking that the eggs are soft and leathery, kind of like a woman's leather purse. That's what they feel like. They're soft and squishy and leathery. So most reptiles do not, lizards and snakes do not have hard calciferous eggs. The reason I only gave that a 95% true is because of alligators. Alligator eggs are also not the same as bird eggs, but they're not soft and leathery. So if you've got lizards and snakes having leather over their eggs, and you have birds having calcium carbonate over their eggs, alligators and crocodiles have both. They have a leathery layer on the inside, which is covered by what you think of as a bird's eggshell. So yeah, they have them. They're not the same as bird eggs, but they do have calcium carbonate. Okay, so we've done 4 traits that largely, but not 1,000,000,000%, distinguish birds from other living vertebrates. Let's talk about 2 traits that do 100%. That's why I've got in caps. Birds have what I call the amazing two-way lung. Okay, it's my favorite trait that birds have. And if you think about it, birds have very high oxygen needs. They have very fast metabolisms. Flying takes a heck of a lot of energy. And when they fly, sometimes they're really high up in the air where it's cold and the oxygen is lacking. So all in all, they have to be really good at taking oxygen into their system. And the way they do that is by having sacs that are not lungs, but they're attached to the lungs that serve as a secondary source of oxygen. Here, it works like this. Okay, think about yourself. When you breathe in, you take oxygen in, and when you breathe out, your lungs empty, and you breathe out carbon dioxide. So you're only taking in oxygen, and all mammals are only taking in oxygen 50% of the time. Only when you inhale, not when you exhale. Birds take in oxygen 100% of the time, because when they breathe in, the air goes into their lungs, and some of it then passes into these sacs that are attached to the lungs. But those sacs are not made of lung material, and they do not absorb oxygen. So I get my normal shot of oxygen, but when I breathe out, the air that was in those sacs passes through the lungs, and the oxygen gets absorbed. So they get oxygen 100% of the time. They take in twice as much oxygen as anybody else does. And that's what allows them to burn the kind of energy they need to burn in order to fly. So, and no other animal has that. Okay? No other living animal has that. So that's pretty good. That's one most people don't know, but it really is a distinguishing trait of birds. And finally, feathers, which is the one most people point to, and it's totally right. If you see a living animal that has feathers, it is a bird. Okay? No ifs, ands, and buts about it. Birds are the only living animals that have feathers. We're going to talk more about feathers later. There are all different types of feathers, but whatever feather you look at, only birds have them. I did want to point out to you, though, that birds also still have scales. Yeah, this is a bald eagle's foot, And you can actually see, I can't point it because I can't move, but it's actually got two different types of scales. On its toes, you can see flat scales. Those are very much like what lizards and snakes have. If you look higher up towards its ankle, you see pebbly scales. Okay, those are very different. Those are more what alligators have and what dinosaurs had. So they've still retained some scales, even though they have feathers. And it's not just their feet, because there's a black vulture and you can see the pebbly scales on its head. So yes, they have feathers. They don't necessarily not have anything else. Okay, so we've just gone through 6 traits, and I would basically say, if you compare birds to other living vertebrates, it's 0 for 6. I mean, they are different in all 6 ways. There's no overlap. How about dinosaurs? You knew I had to get here. How about dinosaurs? Wings? Well, we know of more than 50 species of dinosaurs that had wings. When I say dinosaurs, I mean non-avian dinosaurs. Non-avian dinosaurs is just too long to say. So when I say dinosaur, I mean non-avian dinosaur. Hard toothless beaks were very common. I'll show you a picture or two of that. Many dinosaurs had hollow bones. I'll show you a picture of that. Calciferous eggs, until very, very recently, like 5 years ago, paleontologists used to say that in order to be classified as a dinosaur, you had to lay calcified eggs. I mean, it was considered a definitive trait. Now we know that the very earliest dinosaurs did not. But once you get past the very earliest dinosaurs, they all had calciferous eggs. Two-way lung, yes, they have them too. Not all dinosaurs, but lots of dinosaurs have that amazing two-way lung. And feathers, hell yes. So instead of 0 for 6, we're 6 for 6 with birds overlapping with dinosaurs. So that's my attempt to try to prove to you that birds are in fact much more closely related and more similar to dinosaurs than they are to anything else. Certainly way more than they are to mammals, for example. Okay, let me just show you some pictures that illustrate this, okay? There's a model of a stegosaurus, and again, you can see that it ends in a hard toothless beak. I'll show you more pictures of, no, I can actually show you another one now. Got 2 different dinosaurs here. There's a hadrosaur, duckbill dinosaur, that you can see had a completely toothless, hard beak. Doesn't look like a bird beak, but it is a hard toothless beak. And the other is actually some sort of saurian, some sort of a apatosaurus type, brontosaurus type dinosaur. And it had a full set of teeth. But if you look at the wear pattern, look at the teeth. It's shiny on top and then not shiny towards the end of the teeth. That's because they had a partial beak that covered the top of their teeth. So they had the beginnings of a beak. What's interesting about this is none of those 3 dinosaurs are anywhere. They're nowhere near the dinosaurs that are related to birds. So it's not just the dinosaurs that evolved into birds. It's like dinosaurs at large had some of these traits. What else do I have here? Oh, feathers. Okay. I love this picture. And the reason I love this picture, that's T-Rex, is I grew up in New York City and I used to go to the American Museum of Natural History on the West Side all the time. That's how I learned to love dinosaurs. And about 5 or 6 years ago now, they closed for 2 or 3 years. And they totally redid their dinosaur hall. And now when you walk into the dinosaur hall, there's their T-Rex covered with feathers.
Please. The time is now 7 p.m. and this branch of Regional Library is closed.
Okay.
Please collect your personal belongings and exit the building at this time. The library will reopen tomorrow at 10 a.m. Have a great night.
But we can stay. So we got the T-Rex here, and you have to understand the American Museum of Natural History is as mainstream, well-respected, and solid as you get when it comes to dinosaur stuff. So the fact that they did this is actually a very telling thing. Not only do we have the grown-up T-Rex, but they also have cute little baby T-Rex there covered with downy feathers like baby birds are. So yeah, lots of dinosaurs had feathers. In fact, I got one more picture, I think, here and some others later. It's not just the American Museum of Natural History. This was taken in the Austrian National Museum of Natural History. And you can see that they prominently feature a feathered dinosaur that they're calling a bird. Okay, now the next picture really isn't very good, but it's the only one I could find. I wanted to just show you that hard calciferous layer is visible in this fossil. And again, except for the very earliest dinosaurs, dinosaurs had chicken eggs. I mean, in effect, chicken eggs. And lastly, this is an early Brontosaurus-like, a saurian dinosaur. And again, nowhere near related to the dinosaurs that evolved into birds eventually, but it also not only had hollow bones, it had that amazing two-way lung. In fact, that's what allowed, they think, dinosaurs, you know how big brontosauruses are, right? Apatosauruses are, I mean, those are huge, like the size of a large whale. I mean, they're enormous. The only reason they could grow that big was after they developed the two-way lung and hollow bones, because that's what let them be lighter weight and lets them take in enough oxygen to support such a big body. So very important, and again, widespread throughout the dinosaurs. So just to beat this dead horse a little bit more, there you go. If you compare birds to dinosaurs versus comparing them to other living vertebrates, there is no doubt that birds are much more like dinosaurs. In fact, the same as dinosaurs, non-avian dinosaurs, compared to anything else. Okay, so there's my start. The next thing I want to do is I want to talk about what is a dinosaur anyway? I mean, if we're going to talk about how did birds evolve from dinosaurs, we should establish what makes something a dinosaur. And I think a lot of people, when you say the word dinosaur, they just think of any old reptile that lived a really long time ago. You know, if you lived in the Mesozoic or the Triassic and you were a reptile, then you were a dinosaur. But that's not true. Dinosaur is a very specific type of reptile. It's an order. Okay, if you know kingdom, phylum, class, all the way down to genus and species, they are an order. And so they have characteristics that set them apart from other early reptiles. First off, dinosaurs evolved about 240 million years ago in the right at end of the early beginning of the mid-Triassic. The non-avian ones died out 65 million years ago. So dinosaurs lived for 175 million years. They were whoppingly successful. They were the dominant creatures on Earth, and they were the dominant creatures on Earth for a heck of a long time. We'll come back to that. So they were very long-lived and very successful. Now, there's lots of things that set dinosaurs apart from other reptiles, but most of them are internal things that if you weren't an anatomist and didn't do a dissection, you wouldn't know. But there's one cheap, easy way to always tell a dinosaur when you look at a lizard, when you look at a reptile. And here it is. On the left, we have an apatosaurus, saurian type dinosaur, and on the right, we have a crocodilian. Actually, it's an alligator. Notice the difference in the legs. Dinosaurs are reptiles whose legs go straight down under their bodies. All other reptiles, both extant and from a long time ago, have splayed legs like this that you're seeing in the crocodilian. So if the legs go straight down like a tiger's do, then it's a dinosaur. If the legs don't, then it isn't. That's really easy to tell. By the way, that's Gigantoraptor, which was a really nice dinosaur that happened to be heavily feathered. On the side, and you can see its legs also go straight down. All dinosaurs have legs that go straight down, and no other reptile does. That's how you can easily tell. You look at you go to a museum and you look at a fossil, a skeleton there. Is it a dinosaur or not? That's what you look for, and that'll tell you. Okay, well, now let's trace how you go from dinosaur to bird. Okay, how did that happen? But being a very linear person, I have to start a little earlier than just with dinosaurs. So I'm going to go back a little bit before we get to dinosaurs. I'm going to start with reptiles, okay? Because birds evolved from reptiles. This guy is Hylonomus. He's arguably the first reptile. There may be others we haven't discovered yet, but right now that's the earliest one that we know. And reptiles evolved from amphibians. And the big difference between amphibians and reptiles is that amphibians are tied to water. if you're a lot of them, like frogs and newts, have to be in water a lot of the time. Toads don't have to be in the water so much, but they have to breed. They breed by going back to the water. So really what made reptiles different were they were what we call amniotes, meaning that they had those enclosed eggs that didn't dry out. They could be laid on land. And the reason this mattered and was so successful is that you know all about plate tectonics. The planets, the continents are always shifting and getting closer to each other and going apart again. The first reptiles evolved on the heels of a mass extinction, one, so that the land was empty. There had just been a mass extinction. Part of what was going on with the mass extinction is the continents all pushed together. So you had one or two huge supercontinents rather than 7 or 8 small continents. What that means is there was a heck of a lot of dry land. And I mean, think about it. Think about where the deserts are today on Earth. They're in the middle of this country. They're in the Sahara, in the middle of Africa. They're the Gobi Desert, the middle. Deserts tend to be in the middle of land masses, because if you're along the edge, then you get ocean breezes, which have water in them, which have moisture. So all of a sudden, there was all this dry land. And there's one thing Mother Nature hates, it's a vacuum, right? I mean, if there's all this dry land and nobody living there, something's going to evolve to make it. And that's what happened. That's why reptiles evolved. Okay. So this happened. Hylonomus was about, did I say this, about 8 inches long, an insectivore. He evolved about 315 million years ago. In what is a blink of an eye to an evolutionary biologist, because the land was empty. There were niches to exploit. These stem reptiles very, very quickly spread out and evolved and changed and became different types of reptiles to exploit different niches, different habitats. And so they very quickly evolved rapid radial evolution into 3 different superorders. And I'm going to go through each of them. The first one are the archosaurs, and that's the one I really should stick to, because archosaurs eventually gave rise to dinosaurs, who eventually gave rise to birds. So I'm going to go back and talk about the others for just a minute. Again, 315 million years down to 310 million years, 5 million years. This is nothing in evolutionary time for this to happen so quickly. So if you look at the archosaurs, archosaurs themselves, once they've been around a while, differentiated into different orders of archosaur. The first one that showed up were the turtles. Then came dinosaurs. Then came crocodilians. Then came pterosaurs, pterodactyls, if you prefer that name. And then plesiosaurs. Plesiosaurs were reptiles that they were aquatic reptiles. Think of the Loch Ness Monster. Okay, the Loch Ness Monster, Nessie, looks like a plesiosaur. Okay, I mean, flippers and, a long neck and a big fat body, okay. And then, of course, dinosaurs, after some period of time, evolved into birds. So birds have been around for about 160 million years. Notice what I'm telling you slyly here is that birds, well, first off, those of us who grew up with bad science fiction movies where they used to dress up a monitor lizard close up and call it a dinosaur, kind of think that dinosaurs are big lizards. Dinosaurs were not big lizards. In fact, they were far more closely related to both turtles and crocodiles than they are to lizards, because lizards are not archosaurs. They're not on my list here. Okay, so dinosaurs were not giant lizards. If anything, they were giant crocodilians with long legs. Would be much, much more accurate. Okay, so anyway, we'll come back to this, but I did want to mention the other 2. Okay, over here, over on the right, we have lepidosaurs. And lepidosaurs, which evolved after the archosaurs, just a little bit, but after, are basically, I mean, you've got an analogous pattern here. Archosaurs became dinosaurs, became birds. Lepidosaurs became lizards, became snakes. Okay, it's an entirely different lineage, okay, not related to dinosaurs. Note that lizards are a newer invention than dinosaurs, and snakes are a newer invention than birds. which usually surprises people. They assume birds have to be newer, they're warm-blooded and they're smarter, so of course they're newer, but they're not. Very quickly, what makes a lizard and why are they not like dinosaurs? First off, there's the legs again. On the left, you've got a hadrosaur. Look at the legs going straight down. You've got, that's a bearded dragon from Australia, and you can see its splayed legs. We got that. The skin is different. Lizards and snakes have flat scales that are shed as a whole or in big chunks. Think about snake skins, they all get shed at once. Whereas dinosaurs have a different type of skin covering. We call it a scale, but a more correct name for those of you who know this stuff is scute. They come from a different layer of the skin. They shed one by one. And so that is actually a piece of fossilized, mummified dinosaur skin. And you can see it looks a lot like crocodile skin because they also have scutes. So anyway, scales versus scutes. There's a, I don't know why I have this one in here, but there's a living alligator. And again, our black vulture with its scutes showing. I'll do this one real quick, close your eyes if you're modest, but the third thing that really distinguishes lizards from other reptiles, lizards and snakes from other reptiles, certainly from dinosaurs, is they have two penises as opposed to the normal one. When I used to belong to the American Herpetological Association, I'll get rid of this slide. The American Herpetological Association, we teenagers loved wearing our shirts that said, snakes and lizards have something extra, wink, wink. So yeah, so it's a totally different line. That brings us to the third big branch, which are the synapsids. There's a synapsid. Dimetrodon's kind of the classic one. Dimetrodon was about 280 million years old, so older than dinosaurs. This is the line that led to mammals. If you trace back from you'd eventually get to something like him. You get to a synapsid rather than an archaeosaur. The interesting thing about them, one is that they led to mammals, but from the very get-go, I don't know if you know this about mammals, but most mammals are nocturnal. Okay, they're more nocturnal mammals. Birds are almost all birds, if you leave owls out, are diurnal. Mammals are much more likely to be nocturnal. These guys were nocturnal from the very beginning. You can tell by their eye sockets, the size of their eyes. They started off with splayed legs, though they eventually will move under the body. Now, I added this slide new because someone always asks me this, so I'm trying to preempt it. People always say to me, well, so you find some bones or you find a skull, how do you know if it led to birds and dinosaurs versus to mammals? And the answer is really very simple. Synapsids that led to mammals have, you see the nose socket and the eye socket, they have one extra hole in their skull, whereas the sauropsids, which is everything else that's not going to turn into a mammal, has two extra holes. But anybody who knows that can pick up a skull and say, aha, that's going to lead to a mammal or not. It's very easy if you know what you're looking for. Someone always asks me that. Okay, last thing before, last part of my little digression here. Come on, you're here somewhere. I can't find this. You got to be here. There you are. Okay, I wanted to talk about mammals because most people that I talk to believe that mammals kick dinos' butts. And part of the reason that dinosaurs didn't survive is because mammals came along and killed them off. You could not be more wrong if that is what you think, okay? So mammals arose from synapsids, we just talked about that. They evolved at the beginning of the Triassic, so they're older than birds and about as old as dinosaurs. They lived with dinosaurs for more than 150 million years. It is not the case that mammals showed up and there went the dinosaurs, okay? It's not even close to that. In fact, it's the opposite, because when dinosaurs first got going, they got going very slowly. They were not the dominant life form. And at that time, mammals were big and diverse and lived in lots of different niches. As dinosaurs grew bigger and more dominant, the mammals shrunk, and began to survive around the margins. You all know Charlotte's Web? Temple to the rat. That's what you should think of when you think of a primitive mammal during the age of dinosaurs. They were, I like to say, sneaky little buggers. They lived by keeping out of dinosaurs' way. They were nocturnal. They lived in burrows underground. Dinosaurs don't go underground. They lived in the trees, and they basically snuck out at night and carved out a living when the dinosaurs were sleeping. And so mammals did not have anything to do with the death of dinosaurs. It just didn't. Yeah, just I have to say that. Okay, what do I have next? Okay, now we're getting back to, so where did birds come from? So we're back to dinosaurs, right? Well, paleontologists divide dinosaurs into two different suborders. You can divide them in half. And why do I have that X there? Oh, I know why I have that X there. I'll go back. Now I know why I have that X there. Okay, when most people think, if I just were to say to you with no prelim here, divide dinosaurs in half. What most people say is, well, you've got two-legged carnivorous ones and four-legged herbivorous ones. Certainly the two-legged ones and then the four-legged ones, and so that's how you divide them in half. No, unfortunately, it's logical, but it's not correct. So I've got this slide. Both of the two suborders had two-legged and four-legged varieties. So it isn't that. It all has to do with the structure of their pelvis. Their pelvises were very, very different. So if I trace birds back, I know which half to go to. And though you'd guess that they came from the bird hip dinosaurs, ornithischian means bird-like, they in fact came from the ones that had lizard hips, saurischian hips. And only later did those hips turn into bird hips. So it's the saurischian dinosaurs, Allosaurus being a good example of one, that are the line, the suborder that's going to eventually lead to birds. Okay. So which saurischian dinosaurs became birds eventually? And the answer to that is theropods. Theropods are a family of dinosaurs. And when you think of that, that's an Allosaurus. When you think of theropods, most people think of T-Rex first and foremost, maybe Spinosaurus, maybe Allosaurus, maybe Velociraptor, like they showed them in the Jurassic Park movies, which is really inaccurate, but that's what people think of. And so that's what you're thinking of. Those are the ones that evolved into birds, and they did. And it's very hard for people to imagine how that happened. I get it. It's hard for me to imagine how that happened, except I know some stuff that you don't know yet, which is that's also a theropod. The theropods most people are familiar with are the really mega big ones, but lots of theropods were small and agile and covered with feathers. And when you start thinking of a theropod like that versus like T-Rex, it's much easier to imagine that you can go from that to a bird. And if you look at the theropod family, what you find is that there is all different, that's just a fraction, all different types of theropods. Theropods are among the most long-lived from the beginning to the end of the dinosaur age. They were there virtually the whole time. They're the most numerous type of dinosaur. We have found more species and more individual theropods than any other type of dinosaur, well over 100 species. And a lot of them are really little. It's just those aren't the ones that have kind of caught the public, right? They're not monster movies and stuff, so people don't think about them. Okay. Excuse me, I misspoke. There's not 100 species of dinosaurs. There's more than theropods. There's more than 1,000 identified species of theropods. So they were very common, very diverse. They ranged in size from about 3 inches to 50 feet long. They started off all being coniferous, but by the end of the age of dinosaurs, a lot of them were omnivores, so very, very diverse. Now, so that's what, I'm going to move away from the mic for 1 minute and point. That's where birds came from the little tiny theropods. Now, where they didn't come from, just to reiterate, are pterosaurs, all right? Pterosaurs may have been flying reptiles, but they are not related closely to birds. They're more closely related than lizards, but they're not closely related to birds. Again, it's an entirely different wing. Pterosaurs lived about as long as dinosaurs, showed up more or less at the same time. A lot of them had toothless beaks. It's another reason you might think they led to birds. But that's convergent evolution, to have lightweight Another interesting thing about the pterosaurs, which might make you think that they're related to birds, is that a lot of them were feathered. Okay, which shows that feathers evolved multiple times during evolutionary history, because these guys did not evolve into birds, but a lot of them were feathered. This one happens to have teeth, but a lot of them didn't have teeth. They had beaks. So anyway, not pterosaurs, not pterosaurs, but theropods. That's what we're going. Now, other ways that I haven't emphasized that birds are similar to theropods. We've already talked about hollow bones, but warm-blooded. We now know that theropod dinosaurs were warm-blooded. There's a lot of converging evidence for that. The two that I like best, one of them is illustrated there, is one, their growth rates. Warm-blooded animals grow much more quickly than cold-blooded animals do. And if you look at dinosaurs, baby dinosaurs, as they grow of different ages, they're just growing really quickly. And so that be associated with warm-blooded. But my favorite piece of evidence is this. Leave dinosaurs out of it. If you've got a cold-blooded predator and prey, it doesn't take a lot of energy to support a cold-blooded animal. So what you tend to find, if you find a collection of fossils, is equal numbers of predators and prey, okay? There are about as many snakes as there are frogs. They just don't need to eat a lot. Warm-blooded predators, on the other hand, tend to need to eat a lot of food. And so what you find, there's one lion for every 10 or 12 zebra. Well, if you look at dinosaur fossil collections, that's what you find. You find the same 1 out of 10 or so ratio. That's very compelling evidence that they're warm-blooded, that they're active. There's lots of technical reasons for it, but let me tell you, those limbs under the body means you're built for speed. Certainly much faster than a lizard doing this. They have, their egg colors. This is trivial, but I like it. You all know that bird eggs don't come in every color of the rainbow, right? You can think about bird eggs. They're whiter, they're cream, and maybe they're robin's egg blue, and they're sort of speckled sometimes, but they're not pink and they're not purple. I mean, they're not electric yellow. Dinosaur eggs were exactly the same range of colors that bird eggs are. Expanded vision and memory lobes in the brain, not as expanded as birds, but you can see it going in that direction. What parts of their brain are big? They had 3 toes. And then there are a lot of behavioral similarities. For example, many birds, as you know, are highly social, right? They live in huge flocks. So were a lot of dinosaurs. You know that by how many bones you find together. You know that by tracks. If you see tracks that they made in the mud, you can tell there are at least 75 individuals, because their feet are all different sizes. And so some of them were highly social and lived in herds or flocks. I like this one, brooding behavior. You know that birds, modern birds, adopt there is a posture that they get into when they're sitting on eggs. And what they do is they crouch over the eggs and they take their wings like this and cover their wings. We found fossilized dinosaurs there on the right, look, that are doing exactly the same thing. They've got the exact same brooding behavior. And you can see it's a dinosaur, it's got long claws hanging down. Another example, sleeping position. Not all birds, but most birds, when they sleep, tuck their head under their wings. Right, there you go, lots of different birds tucking their heads under their wings. That's a dinosaur fossil on the left, and there's a reconstruction on the right. You can see it's got a wing, and it's tucking its head under its wing in exactly the same way. So there are lots of things like this, and I'll stop there, but there are lots of things like this. Okay, you're not going to remember this, but I got to do it anyway. The order in which bird-like traits appear. Feathers, legs under body, and bipedal are traits that are found all through dinosaurs. No matter what kind of dinosaur you look at, hadrosaurs, stegosauruses, ankylosauruses, some of them have had those features. The next 2 lines where it's kind of blue-gray, those are traits that you find in theropods. So hollow bones, wishbone, 3-fingered hand, bird pelvis, flight, and pygostyle. I'll go back and explain what some of those are. And then finally, only the bottom line are things that distinguish birds from theropod flying dinosaurs. Clawless wings, a keeled sternum, and a completely toothless beak. So let's talk about the important ones. There's some of those. So anyway, gradually, these are the features that accumulated that got you from a dinosaur to a bird. Okay, I wanted to talk about the wishbone. There on the left is a human with the clavicles in green, you know, your collarbones, and you all know this, there's a notch between them. They're not attached. That's why you can feel a hollow right here. When you take your turkey, your Thanksgiving turkey, and it's wishbone, what that is the clavicles that are fused together in the middle, unlike ours. And the reason that happened, the reason birds evolved that trait is flying, again, is very tough. I mean, it's a lot of work to fly, and you're putting a lot of pressure on your bones and your muscles. And so it's just simply stronger. When you fuse them together, it's mechanically stronger than when they're separate. And so as birds became more and more adapted to fly, they needed more strength. And so you had that fused clavicle. Pygostyle, on the left is a picture of a rooster. On the right is one of the microraptors. And look, a rooster looks like it has a tail, and it does, it's got tail feathers, but really it's only got a stubby little set of bones that are supporting those feathers, right? That's the pygostyle. Dinosaurs, even the ones that could fly, tended to have long bony tails, like a dog or a cat, where the bones go all the way the length of the tail. And so the evolution of a pygostyle was something that came in at the very end. There are some dinosaurs that have pygostyles, but that's the very, very ones right before birds that have pygostyles. Another one I mentioned, you may not know what I was talking about, is a keeled sternum. That's a chicken on the left and a dog on the right. And again, flying takes a lot of muscle. It takes a lot of strength. And so you all know when you look at a turkey breast, it's got that bone that sticks out, right? That's its sternum. Your sternum, a dog's sternum, is totally flat, okay? But you don't have really big chest muscles compared to a bird. Birds have really big chest muscles, and really big muscles need a place to attach to bone to, and that's why you get this keel. Any animal that has a keeled breastbone, you know, is an animal that was built for flying. So that's where that comes from. All right. The path from dinos to birds. What I wanted to say here is, if you were to go back to the age of dinosaurs, especially the later half, the second half of the age of dinosaurs, the sky was filled with flying things. Not only flying insects, but lots and lots of pterosaurs. They were very, very common. Lots of flying dinosaurs, animals that really were dinosaurs and could fly. Birds, and what I call halfways. Halfways are animals that, you know, evolution experiments, it tries things and then it rejects them, that were halfway between birds and reptiles. It's hard to say which they are because they're halfway between. Let me show you in two different ways you can be halfway between. One is like this. I'm using a horse just because I had a good picture of it. A long time ago, there was an animal called Eohippus, which means dawn horse, that eventually over time changed and became our modern horse. So we all agree that number 5 is a horse. We probably all agree that Eohippus isn't a horse. But are you willing to call number 4 a horse? Or number 3? It's arbitrary. I mean, it's gradually changing. They're becoming more and more horse-like. At what point? God didn't come down and tell us at what point it's now a horse. People make that decision. And so sometimes there's disagreement because I think this trait's more important. You think that trait's more important, you know, whatever. So first off, you get this gradual change. They didn't lose that long bony tail and turn it into a pygostyle overnight. It got shorter and shorter and shorter and shorter and shorter. Well, what's short enough to be called a pygostyle rather than a tail? You know, that's an arbitrary decision. And then you've got halfways like this. If I forced you to guess, are you looking at a bird or a cat? And the answer is, I can't tell you that, right? Because it's got a beak and feathers and wings. So it's a bird, but it's got fur and 4 legs and cat ears. So it's a cat. There are a lot of creatures like this that in some ways are so dinosaur-like. I mean, they're perfect dinosaurs if you look at these 3 traits, and they're perfect birds if you look at these other 3 traits. They're all these halfway animals. Okay. So having said that, what made a bird a bird? What's happening so that some dinosaurs are turning into birds? Well, the overarching picture is that they're getting better and better designed to fly. Not all birds fly now, but to be a bird means you were designed to fly. And then maybe secondarily, other things happen. So in order to fly, you have to be lightweight. So their bones got smaller and thinner over time. Their tail is reduced to a pygostyle rather than lots of heavy bone. You lose your teeth, which are really heavy, and replace it with a beak, which is much lighter, and you get smaller. Okay, so this is some of what was happening to make things a bird. To put this in perspective, if the average man, 5'11" man, remember this figure, 5'11" man wanted to fly, being a man, but he wanted to fly, he'd need a 44-foot wingspan in order to do it. I mean, you know, it was important for them to get lighter so that they could lift themselves off the ground. The second thing that really fed flight is that their arms and chest became stronger because, again, flying takes a lot of work. So stronger arms and shoulders, they get that wishbone and sternum we were talking about, and their arms become longer and stronger than their legs. Okay. In most mammals, for example, legs are much longer and stronger than arms, or at best they're the same. But in birds, you know, they're top heavy. I mean, it's all in the arms. Okay, I'm winding down. Oh, feathers improved. I can't kind of say that. I forgot about feathers. Feathers improved because if you're going to fly, flying, if you've got a bird kind of wing, depends upon feathers. And there is a really nice picture of this is actually a fossilized dinosaur. Look at the tail, where you can clearly see there was no doubt that they were feathered dinosaurs. What else are you looking at there? Okay, I mean, you can see the feathers. It's got feathers. It used to be thought, there's all different types of feathers. It used to be thought until like 3 or 4 years ago, that only birds had true flight feathers. Dinosaurs had all the others, birds have all the others, but only dinosaurs had number 7 true flight feathers, which are asymmetric and hence stronger and better support flying. Now we know there were some dinosaurs that actually had true flight feathers, but feathers got better and better and better. Again, there were lots of feathered dinosaurs. There's a hadrosaur, believed to have been completely covered in fur, not a theropod. This was a dinosaur, which one is, oh, this is Kehong-Jui. I never can pronounce that, about 100 million years old. That's actually correct colors. It was this heavily feathered, and those are the correct colors. They can do biochemical analyses of the fossil and determine what color it was. It has pygostyle, but it does not have true flight feathers, but it had iridescent feathers up front like a hummingbird. So they really were this brightly colored. Here's another feathered dinosaur. This is a microraptor. It did have true flight feathers as well, but what's really cool, and I don't have time to talk about this today, is note it almost has 4 wings, not 2. There were a whole lot of dinosaurs that had leg wings as well as arm wings. Tell me they weren't on their way to flight. Okay, you got 4 wings instead of 2. Speaking of flight, I keep saying the whole point is that dinosaurs, what makes you a bird is that you're designed for flight. Why did flight evolve? How did flight evolve? Very simply, there are different perspectives and they all might have some truth to them. The earliest perspective is that having wings and feathers means that when you run and you get some lift, you can jump higher than you otherwise would, which is really nice if something's chasing you, you know, that you can jump 4 feet instead of 2 feet. So that's called cursorial theory. Then there's the opposite, arboreal theory, and that's a brown creeper, and I've got him there because he lives this lifestyle. The arboreal theory of flight is that what happened is that birds or dinosaurs would drag themselves up slopes, drag themselves up trees, and then sail down, which if you know anything about brown creepers, that's how they make a living. But the current theory, and the one that I believe, is called WAIR, wing-assisted incline running. And you can see videos of this on the web. It's really fun. Go to YouTube. You can find videos. There's a researcher, there's several now, but the first one was a guy named Dial, who he did a really interesting thing. He took various species of baby birds and chased them, scared them so that they would run away. And he had inclined planes for them to run up. And if he let them have their wings free, Some of them could even run up slopes you can see that are more than 90 degrees, as long as they flapped. If you tied their wings to their body so that they couldn't flap, they couldn't get past like 30 degrees. So it isn't lift, it's actually downward thrust that's gluing you to the surface so you can run up a tree to get away from a predator. That really may be what was going on with birds. Anyway, that's the hot theory right now, and I happen to like it. Time is okay. I'll keep going. Okay, early birds in the age of dinosaurs. Again, birds coexisted with dinosaurs, for 95 million years or so. I should say, I'm not going to say much about this. I have a whole other talk on the birds that lived with dinosaurs. This is kind of part one in the series, and that's part two. But just to give you a taste of it, the first true bird, and I've got an asterisk there because it's not 100% agreed on. I'd say a large majority of paleontologists say this is the first bird, but it's not 100% accepted, is Aurornis. Aurornis is about 160 million years old, the size of a pheasant. He had downy feathers that covered his body, probably couldn't fly because down doesn't support flight, had teeth, but that's probably, right now, most paleontologists will say this is the earliest bird we know about. Again, 160 million years, dinosaurs died out 65 million years ago, 95 million years of birds plus dinosaurs living at the same time. For a long time, people thought the earliest bird was this guy, Archaeopteryx, and he's very famous. I mean, Archaeopteryx is if you know any fossils, that's one you may know. And it was long considered the earliest bird, dating from about 150 million years. It's been dethroned in a lot of ways. One is there's Aornis. But besides that, if it was discovered now, rather than in 1860, we'd call it a dinosaur. Almost everybody would say it was a dinosaur, not a bird. Because if you kind of count up the traits, it really does lean towards dinosaur. But the reason I wanted to mention him is this was one of the most important fossils ever found. There's 5 or 6 examples of Archaeopteryx because Darwin had just published his theory of evolution in the early 1860s. And then they discovered Archaeopteryx like the year after. And it's like, oh my God, here is an animal that's evolving. And it was really taken very seriously at the time as really good evidence for Darwin's theory of evolution. So it has a lot of historic importance. This is what they really looked like. If you reconstruct them, that is the correct coloring. They were colored like magpies. They could fly, though probably not super, super well. They had teeth, as you can see. They had wing claws, as you can kind of barely see. But that's another talk, as I said, all about Archaeopteryx. The most common birds during the age of dinosaurs were these guys, Enantiornithes. This is an order of birds. So there are lots and lots and lots and lots of them. These are, think songbirds, think passerines. This is the dinosaur age equivalent of passerines. And if you kind of a normal bird that's everywhere and fills all sorts of niches, that's what the Enantiorniths were like. They were not directly related to our modern birds, though they were great flyers. They had teeth. We know they weren't for several reasons. One, they had teeth. 2, they had claws on their wings. But most importantly, and this is what the name Enantiornith means opposite shoulder. Their shoulders are all wrong. We know they didn't evolve into modern birds. Think about your own hips. If this is an analogy, but it works. Think about your own hips. You've got a femur, a leg bone that has a ball on it, and it fits into the socket of your hip, right? These guys are the opposite. They have a hip bone that has a ball coming out, and it fits into the socket of the femur. Except we're talking shoulders, but you get the point, okay? So it didn't switch. it didn't switch. So these guys all died out. I just had to show that picture because they did live during the age of dinosaurs and filled the same niches. Now, what happened to them? The same thing that happened to dinosaurs. 66 million years ago, a meteorite that was 4 miles in diameter, going 40,000 miles an hour, struck Earth. When it struck the Earth, it left a crater 110 miles in diameter, and with a force that was, they estimate 2 million times the force of our strongest atomic weapon. The shock wave went out 900 miles from all sides. And a heat wave went out, debris everywhere. Basically, well, there were earthquakes, there were volcanoes that triggered 1,000-foot tsunami, excuse me, 1-mile-high tsunamis, they're now saying. And so the world fell apart. The world fell apart. The air was filled with poisonous gases, and which then fell as acid rain and destroyed the ecosystem and all the water. And then because there was so much dust in the air, there was a nuclear winter and most of the plants died out all over the planet. Plus there were worldwide forest fires. Every single forest on the planet burned down, which is why the Ananthian moths all died out, because they're all mostly forest birds. And there you go. The question, people always wonder why dinosaurs died out. What you have to understand is it wasn't just dinosaurs that died out. This was a mass extinction. 75% of every animal on the planet died out. And basically the only ones that survived were smaller than a shoebox. That's going to leave out most of the dinosaurs right there. Did not live in the forests. Generally had underground burrows and either ate underground bugs or seeds, because plants can die and their seeds live. So if you're a seed eater, the seeds last a long time, could eat seeds, or you lived in the deep ocean. That was shelter. But if you were a lumbering around Tyrannosaurus Rex, I mean, forget it, right? So that's what happened to the dinosaurs and what happened to the Anantians. So let me just finish up. So that's why we have avian dinosaurs now and not non-avian dinosaurs. But I have one last thing to talk about. And that's this, because I've really been focusing on how bird-like dinosaurs are. I did want to talk a little bit about how dinosaur-like some birds were. And one of the things that got me interested in dinosaurs originally was this guy, the terror birds. And they're usually called the birds who ate horses. Now, horses weren't quite horses yet, but they did eat proto-horses. So I still like that title. These were very large birds, a whole bunch of them. You can see they're much bigger than a person. But they flourished mostly in South America. From between 65 million years ago, right after all the dinosaurs killed, they filled the empty niches the dinosaurs had, because they were carnivorous. These were your apex predators in South America. Most of them died out 2 million years ago, though a few of them lasted till about 12,000 years ago. So humans and terror birds coexisted in South America for a few thousand years. And that little insert picture there, this is controversial, but I'm telling you it's controversial, but they found a terror bird skeleton with those 2 little bones in its stomach. Those are human finger bones. Now, it could have been scavenging. I mean, so you don't know that it was predating, but you have to explain how these finger bones ended up in there if it wasn't going after humans. They were largely originally confined to South America, which was an island because the sea level was higher. So there was no Central America. But as the world got colder and polar ice sucked up water, you now have a land bridge. And once there was a land bridge, terror birds moved up into North America, and all sorts of North American things, including carnivores, mammalian carnivores. There were no mammalian carnivores in South America originally. They all died out during that big cataclysm, started coming down. And terror birds may have been scary, but they weren't as scary as saber-toothed cats or dire wolves. So they got killed out, and you can get killed off by them, and you can see it. You can see as the population of saber-toothed cats rises, population of terror birds falls. There's a terror bird reconstruction on the right. That's a real life modern bird called a shoebill stork on the left. I did want to remind you that there are some pretty scary birds still around. There's another picture of him. I love his facial expression. There's another scary bird. Does anyone know what that is? Can you imagine what bird that's from? Yeah, that's a cassowary claw. Cassowaries are actually the most dangerous bird on the planet. They do kill people occasionally, not very often, but they do kill people. When I used to visit Australia and went to the jungle, I was always scared of running into one. And so, yeah, we still have some pretty scary birds around. Not most of them, but some of them. Well, I think I have one more picture. This one's not as scary. It's a type of hornbill. But when the dinosaurs, non-avian dinosaurs died out 66 million years ago, most people would say that the age of dinosaurs was over and the age of mammals began. But I want to point out to you that while there are 10,000, a little more than 10,000 species of birds on the planet, there are only 5,400 species of mammals. And while there are between 200 and 400 billion individual birds on Earth, there are only about 120 billion individual mammals. Birds range from less than 1/10 of an ounce, that's a bee hummer, to over 300 pounds and 7 feet tall, that's an ostrich. Birds live in every habitat on Earth. You can find them in the deep ocean, you can find them in marshes, you can find them in deserts, you can find them in the forest, you can find them in the Arctic, the Antarctic, you can find them pretty much anywhere. So I just want to leave you with the thought that the age of dinosaurs may not really be over. It's just that dinosaurs are smaller and a little bit more feathered than you probably imagine. And with that, I'm done. So thank you for listening.
Right, thanks so much, Kim. I will take some questions in the room first, and then we can go online and see if there's any questions. Anyone have a question in the room?
Probably very basic, but what purpose do the feathers serve on dinosaurs?
Okay.
So like what they serve on birds now?
No, probably not originally anyway. Oh yeah, thank you. When feathers first evolved, it's pretty clear that they did not evolve for flight. Because there are a lot of animals like Triceratops that was certainly not flying that were feathered. Instead, it was either for warmth. I mean, that's one possibility. The other is for display, for mating purposes, you know, look at me, I'm a sexy male sort of thing. And then later, you know, this is how evolution works. Something evolves for a particular reason, and then it gets borrowed for a different reason. So when feathers first evolved, it was not for flight, but later on, you know, it served flight, so they were used for that purpose. Does that answer your question?
Yeah, no, I was assuming it was for, weather.
Yeah, warmth is probably, because a lot of dinosaurs lived in really, again, when most people think of dinosaurs, they think of like humid tropical jungles like you see in Jurassic Park. But a lot of dinosaurs lived where it was really pretty cold, like in Antarctica, which wasn't as cold then as it is now, but still was cold. So yeah, feathers.
Looks like we have a question, what are caruncles?
I'm blanking. Sorry.
Caruncles.
What are caruncles? And I know I should know the answer, but I don't, so.
It's like a waddle or the like red fleshy piece of a bird.
Oh, why did those exist?
Question is just what are they, but do you have any?
I suspect, like with feathers, they serve different purposes. Because in some animals, in some birds, they are used as mating displays, especially if they're inflatable. Some birds, like frigate birds, can really inflate them. They also might be like in pelicans, you know, that you can use the space that they provide for something, but I really don't know the answer, so I don't want to pretend that I do. Sorry.
Question right here.
I'm looking, I wanted to, have you speak at another event. Do you live nearby?
Olympia.
Olympia? Okay, all right, good. I'm told, just pass on local speaker, so I'm gonna pass it on you. This is fabulous.
Thank you.
Yeah.
Question.
There's another one here. Let's see.
There's no answer.
Yeah, that's the ones. Okay. Kevin has one question.
Okay, Kevin, stump the speaker. Go ahead. Stump.
Really interesting, that I've heard about this before. He talks about large early mammals.
Yes.
And I'm wondering if you could like name one. It sounds like you're saying the Triassic type of mammals and they're big. Yeah.
Okay, the dominant animals, okay, we were talking about early mammals being big, because that's something that Kevin hadn't heard about before. Don't ask me for Latin names that I haven't looked up recently, but I can tell you that if you go back to the Triassic, the dominant creatures on the planet were crocodilians. Crocodilians, they didn't look like modern crocodiles, they had very long legs, for example, and were much more mobile, and they didn't all have the crocodilian lifestyle, we think of them submerged in water and, springing on prey unawares. They lived more like you're thinking of dinosaurs living, but they were more successful. Dinosaurs were little, dinosaurs were prey animals, and the same for mammals. Mammals weren't as big or as fierce back then as the crocodilians were, but they were much bigger and more diverse than they were during the height of the age of dinosaurs. They were maybe dog-sized back then, maybe a little larger than a dog, and some of them were carnivorous, some of them were insectivorous, some were herbivorous, and there were all sorts. But really, when dinosaurs were at their heyday, every mammal was like a tree shrew. You know what a tree shrew is? Kind of like, they're not, I mean, they're reasonably closely related, but they're not things like a squirrel. I mean, they were rats. They were sneaky little rats. That's what they were. And then when dinosaurs got killed, they survived that cataclysm, some of them, because they were in their underground burrows, eating worms, which were 6 feet underground and survived, and eating seeds, which lingered when there weren't any plants left. And then they took over the planet, you know. Again, my big point in having said that was that there really is no reason at all to believe that mammals outcompeted dinosaurs. You just can't make a case for that.
Any other questions?
Yeah, one last question. I'm 74 years old. When I went through school a long time ago, there was no talk about birds having relationship with dinosaurs. I'm clear after this that lots of people knew that, but apparently not the people who were teaching me at school. Approximately when did this become mainstream knowledge?
I would say it began to be talked about. It was a fringe view in the 70s. By the 80s, it was becoming more accepted, and by the 90s, it was, this is the way it is.
And that was as humans and dinosaurs.
As birds as coming from dinosaurs. Some of it is, and I didn't have time to say this, is that there has been an explosion in finding small feathered dinosaurs in the past 25 years. And the reason for that is that birds and small feathered dinosaurs don't fossilize very well. If you're small and you have light hollow bones, you're not going to be a fossil as easily as, if you're a big elephant. And so you need a very particular set of conditions for those fossils to survive. And it doesn't happen very often. But there's a place in China where it just has the right conditions. And so when that opened up, there's also some places in Eastern Europe, but most of it came from China. So all these new species, it's really because the Chinese started doing wonderful paleontology.
Yes.
Any other questions?
Kim, thank you so very much.
Oh, you're more than welcome.
Give Kim one more around the clock.
Thank you.
Well, thanks so much for coming, and look forward to seeing you at the next program next month. Check out the Kingfisher when you get it, as well as the website for more information. Hope you have a safe trip home. Bye, everyone online.
Thank you, Mike. Anybody?